is analogous to the Poisson lambda. The binomial n is analogous to the Poisson t, units of contiguous exposure, and then they both have x as the random variable of interest. So let's take a look at our shuttle crash data, okay, using p of 0.0177. In other words, 2 events in 113 missions. And in this case, you can think of the crash as the event of interest, and you can think of your time unit as mission. It's an analogous type of exposure, because what's in the denominator is the exposure. You're not exposed unless you're flying the shuttle. So that's analogous to a time unit, where with continuous time, and we're looking at something like arrivals, people can arrive at any time. So time is a value, or a reasonable exposure variable. But for the missions of the space shuttle, time isn't a reasonable exposure value, because they're only exposed when they've launched the shuttle. So you look at missions as your exposure variable. Okay, so this is 2 events in 113 missions. Missions being our units of exposure. So we can call the 0.0177 a lambda, or we can call it p, a binomial. Now this is, and we've already done this in the next 10 missions. This is what the probability looks like. For Poisson, it doesn't stop at 10; it keeps going. But once again, we start getting diminishingly small values. So I won't bother to go beyond 40, although with the understanding that this can go on into perpetuity. Now our t becomes 10, because that's our units of exposure that we're projecting into the future, 10 units of exposure. And if you look at the first 10 probabilities for the Poisson, and the first 10 probabilities for the, or the 10, or 11 I should say, for the binomial, you can see that the Poisson is a very good approximation. It gets very similar results. It's not the same, but it gets very similar results. So the probability of no crashes is 0.836. Over here it's 0.837. Or if we round to 0.838 and 0.836. But still, you get to the 1,000th before you get a difference in probability. And that's probably not a practical, for this kind of calculation, that's not a practical difference. You can use Poisson to approximate it. And then if you look at the other ones, they're very similar. Okay? This is, when it gets down here to 10, it's to the 3.02 to the minus 18th, and that's 6.96 to the minus 15th. As it gets diminishingly small, it gets quite a bit different. There's a much larger factor difference. But at that small probability, it doesn't make a huge difference. And we really don't care. It's just really small. But nevertheless, Poisson is an approximation. That makes sense? Now, Kyle asked a good segue question as to what happens when this changes. Well, let's look at confidence intervals on lambda, because to build a confidence interval, you need the number of occurrences of the event of interest and the number of units of exposure. F over t is lambda, okay, in the nomenclature that I'm using for the confidence intervals. And the reciprocal, or lambda inverse, is the mean time between failures. And it's usually called mean time between failures because they use this overwhelmingly in reliability engineering when they're interested in failures. You can think of it as mean time between occurrences. That's more of a generic term and more helpful if you're thinking about something that's not a failure. Okay? Arrivals. It could be mean time between arrivals. That's not a failure, it's an event of interest. Mean time between errors. Mean time between crashes. Any number of things. So occurrences is more of a generic term, although you usually will run into MTBF, mean time between failure. And just to show you what a liar I was in quantitative methods, we can do a one-sided confidence interval. But I didn't want to go into that then. For this, a one-sided confidence interval actually makes a lot more sense than a two-sided, because we're usually only interested in one end of the tail. So for a standard two-sided confidence interval, the chi-squared for the lower limit and for the upper limit varies. Okay? And we use alpha over 2 for the lower limit with 2f, in other words, 2 times the number of occurrences of interest for the lower limit, and then for the upper limit, it's 1 minus alpha over 2, and 2f plus 2. So you have to keep track of that to get the right chi-squared values. Okay? And then for the denominator, in both cases, it's 2 times t. So let's look at, I think this is a little bit more intuitive. Let's look at our shuttle data. Okay. Now, if you look at chi-squared with alpha over 2, where alpha being 0.05, so it's 0.025, with 2f degrees of freedom, 4 degrees of freedom, it's 0.48. If you look at the upper one, it's 1 minus alpha over 2, or 0.975, 2f plus 2, so it's 2 times 2 plus 2, or 6 degrees of freedom, that's 14.45. Now, I think I used Excel to calculate these, but those are readily available from the table also, at those relatively small numbers like that. With 4 and 6, you can get it from the table. Now, when we start getting the really large numbers, they won't be available in the chi-squared table. But anyway, let's look at the chi-squared table, just to refresh your memory. I'll leave it. No, I don't have it. Let's not. We'll look at it next week. With the chi-squared table like this, you can get it off the table without interpolating. On the exam, I'll try to give you numbers that are on the table. If they're not, just use the nearest one. Remember on the F table, I said don't bother interpolating it. This is the same thing. Don't bother interpolating. Just use the nearest one.
And tell you which one.
Then tell me which one you used. Yeah, exactly. So the alpha over 2f degrees of freedom is 0.48. So it's 0.48 over 2 times t, which is 113, which is our exposure units. And then for the upper tail, it's 14.45 over 2 times t. Now that means that our lambda, a 95% confidence interval on lambda, will range from 0.0021 to 0.0639. And I took those out to 4 decimal places just because they're relatively small. But if you take the reciprocal of those numbers to get the mean time between occurrences, now remember, when you take the reciprocal, you have to flip the inequality. Right? So I flip the inequality signs, and that's now mean time between occurrences. So that means that it will be between 15.6 missions between occurrences at the lower level, lower limit, to 467 missions between occurrences at the upper limit. That's a very wide interval there. Right? And, we're probably more interested in the lower limit, but then that's two-sided. So let's look at a one-sided, because that's really what we're interested in, is what's the worst-case scenario of this happening. So for the lower limit, lambda is less than, and we use 1 minus alpha sort of based on this upper limit here, 2f plus 2. 1 minus alpha, 2f plus 2, so now 1 minus alpha is 0.95, 2f plus 2 is 6. So 0.95, 6 degrees of freedom is 12.59. Our lambda is going to be less than, 95% is going to be less than 0.0557. And the mean time between failures will be about 18 missions. Okay. So, mean time between failures, 95% of the time is going to be greater than 18 missions, which is now is more useful, it's more interpretable than this one, which is two-sided, and I'm probably more interested in the lower limit there. But if I take my whole alpha and just shove it into the lower, into one tail, and get a confidence, it's not even really called a confidence interval, I mean, technically it's called a confidence interval, but it's no longer an interval. It's just a lower limit. Okay, so that means that we can expect to get at least 18 missions. 95% of the time before we get a crash of some kind at this rate.
And this is, I was gonna ask, this is a 95% confidence interval?
This is a 95% two-sided, 95% one-sided.
Okay.
Yeah. Yeah, because I kind of hit it here, but my output is 4.5.
Right.
Yeah. So what's most easily interpretable is to get your confidence interval on lambda, and then take the reciprocal of it. Mean time between occurrences is by far the most intuitive way to determine or to interpret these ranges on the lambda. Make sense? Yes? No? It's okay? All right, so we'll come back to it. Now I wanted to give you, just for the sake of comparison, some more discrete probability distributions. And I didn't really, like I said, if you look in the catalogs I've seen of probability distributions, there's probably on the order 30 or 40 of them altogether. But I picked out some that I thought were kind of interesting. First one's the geometric distribution. If we have a sequence of Bernoulli trials and P is success, this gives you the probability of the first success in a sequence of Bernoulli trials. So the number of trials required before the first success is X. Okay, so if I want to know the probability, given a certain probability of failure, or a certain probability of success, either way, what's the probability that I will go 10 trials before I get a failure? That's the question that it answers. So let's say that I know that the probability of success in a task, P, is 0.05. In other words, really, really low probability of success. 95% of the time we fail at this. What's the probability that the first success will occur on the third attempt? So, that means that I have to have 2 failures before I get a success. So X is 3, and Q I raise to the X minus 1, and P to the 1. You just because it's always just P times Q to whatever X minus 1 is. So what that means is that I have 2 failures and a success. Right? This is kind of intuitive. You don't even really need the distribution to figure this out. So it's 0.95 times 0.95 times 0.05. Okay, so that specific sequence, and it's only good for that specific sequence, is 0.45, about 0.05%, a little less than 0.05 because it reduces it when you it only occurs on the third trial. It occurring on the second trial would just be 0.95 times 0.05. That's all we're moving to it. It occurring on the 5th trial is 0.95 to the 4th times 0.05. So that's the geometric. There is an extension of the geometric called the Pascal or negative binomial, okay, where we once again have probability of failure is Q, probability of success is P, and X is the random variable of the number of trials required before the nth success occurs. It's hard to say that without sounding silly, but that's just the variable we happen to use. So let's say that I have 20 trials, and I want to know what the probability of getting 5 successes in those 20 trials is. Okay? So that means that X is 20 and R is 5. And that's all I need to know, and the probability of failure and or the probability of success. So, in 5 trials, what's the probability of 3 successes and 2 failures? or I mean, yeah, 3 successes and 2 failures. So we have x minus 1 objects taken r minus 1 times. Because remember that the formula is x minus 1 taken r minus 1 times. And it's combinatorics again. P to the r, p to the x minus r. So p is the probability of success, is 0.4, and you have 3 successes, and 0.6 is 2 failures. This is analogous in many ways to the binomial distribution, because we're using combinatorics, but it answers, again, a somewhat different question than the binomial does. This answers, how many failures am I going to get by the fifth, how many, let's see, r failures by the x, by the time I do x attempts at this task, whatever it is. And this is the typical notation for the Pascal or negative binomial. It's 5 attempts, the number of successes, vertical slash number of successes, and the probability of success, P. So the Pascal or negative binomial is related to the geometric the way the binomial is related to the Bernoulli. And it's a similar type of relationship. In successive Bernoulli trials is a binomial. Successive geometric occurrences are Pascal or negative binomials. This one relates back to the binomial. As the name implies, binomial is 2 possible outcomes. Well, there's a generalizable form of that, which is called the multinomial, where we have any number of possible outcomes. And we have k possible outcomes. And all we need to do is make sure that the probability of our k possible outcomes, all those probabilities add up to 1. So as long as each one of those probabilities adds up to 1, this will work. And so the x is the predicted number of occurrences in each category, and p is the probability, is the a priori probability of that occurrence in each category, as long as all of these add up to 1. So this has to add up to n, the total number, the number of predicted occurrences in each category, and also, even though I didn't put it there, these have to add up to 1, just because you have to account for your entire sample space. And you have an expected value and a variance associated with each occurrence, each category, and the expected value in category X is n times p sub I, or in category I, and variability is n times p sub I 1 minus p sub I. Same as binomial, except now we're extending it to more than 2 occurrences. So, let's say that we have 1,000 flights, and historically, this is what we have observed. For 1,000 flights, we have 3 fatal accidents, 6 quote-unquote major accidents, whatever that might be, 12 quote-unquote minor accidents, and accident-free flights are just 1,000 minus 3 plus 6 plus 12, 979. So that means that a probability of each one of these are listed here. Okay? Now, a question that I can ask then is, what's for 300 flights, what's the probability of 1 fatal, 2 major, 4 minor? And we're assuming then that the remainder are accident-free. Okay, so by subtraction, the number of accident-free flights are 293. So, again, the notation is the number of occurrences in each one of the categories, separated by commas. Given that you know what the a priori probabilities are for each one of those. So, 300 is the total. That's 1 factorial, 2 factorial, 4 factorial, and 293 factorial. See here the elimination works out pretty well. It's easy to factor out the 293 factorial. So we have the probability associated with three fatals. With the fatal is 0.003. That's the first because it's just one occurrence. The probability associated with major is 0.006, and we are curious about two of those occurring. The probability of 4 minor, which is a priori 0.012, and then 0.979 from here to the 293rd. The limitation of this, and that's the probability about 0.02, okay, about 2%. The limitation of this is that you really can't do the easy, under most circumstances, the easy, okay, the complementary, because this is multidimensional. It's not just two occurrences, it's multidimensional. One thing that you can ask is what's the probability of being accident-free in the next 300? And that's a relatively easy question to answer. And I thought I put it there, but the accident-free in the next 300 flights would be 300 over 0 factorial, 0 factorial, 0 factorial, 300, so that goes to 1. It's 0.003 to the 0, so that goes to 1. 0.006 to the 0, that goes to 1. 0.012 to the 0, that goes to 1. 0.979 to the 300. It just reduces to that. Okay. And that is not trivial, but it's a smaller number. Okay, because I know that there are probabilities associated with the other three possibilities. What does it come out to be?
It's 1.71, or 1.72 times 7 minus 3, so 0.00 minus 3.
0.0017.
Yeah.
Yeah. So it's a small probability, but it's something that can occur. It's not diminishing. Okay. It's just very small. And given that I have any probability of these other three happening, that's going to reduce my probability pretty drastically. Of being accident-free, that is. So this is just an extension of the binomial. And if you have two, you can always apply this, because if you have only two occurrences, this will reduce to the binomial. Okay. So let's say that I try to apply this, and I only have two occurrences. So the P1 is equal to, since these have to add up, one is 0.05, I don't have much imagination, P2 is 0.95, and those add up to 1. And that I want to know what the probability is of, in the next 10, of having 6 here and 2 here. And so applying the multinomial, probability of 6 and 2 is equal to, and since those add up, sorry, I can add, just not very well. Okay, so that ends up to 10 factorial, 6 factorial, 4 factorial, and 0.05. So the 6th and 0.95 to the 4th, and that is the binomial. We'll reduce to that. Okay, so that's multinomial. Now let's take a look at something that is quite a bit different than any of them. And this has to do with drawing items without replacement. Okay? Because if I replace it and I have items in a bin, the probability is the same. Okay, you know, if I have 20 things in a bin and there are 3 varieties, well, let's say 4 varieties. There's 5 of each. I'll make it really simple. Okay, so there's variety 1, variety 2, variety 3, variety 4, okay? And there's 5 of each. So I have a 25% chance of drawing any of them when they're all there. If I put it back, my chance of drawing any one of those is still 25%. However, if I draw one and then leave it out, and I draw another one, that's selecting without replacement. Okay? That's what the hypergeometric does. It gives you probabilities of selecting without replacement of each one of them. Okay? And it's what it is, as you can see, a series of combinatorics. So, we have the W's, which are the total of each category of interest. Okay? X is the number drawn in each category. Okay? Remember that all of the W's, W sub i's, have to add up to W, and all of the X sub i's have to add up to X. Okay? So let's say we have 200 parts. It's obvious that I drew a lot of these examples from reliability engineering because we talked a lot about defectives. But when you think about it, defectives and accidents are awfully similar to each other. So there is a relationship. So I have 200 parts, and I want to draw 10 of them. I'm sorry, 200 parts. 6 of those 200 parts are defective and non-functional. There are 8 of them are defective but still functional. They have some sort of an imperfection, but they still work. And the remaining 186 have no defect whatsoever and they're fully functional. So, if I want to know what the probability is of drawing 1 defective non-functional, 2 defective functional, and the remaining defect free, then I know that out of the 6, I draw 1, the 6 defective non-functional, I draw 1, the 8 defective but still functional, I draw 2, and since I'm drawing 7, these have to add up to 10, so I mean, since I'm drawing 10, these have to add up, so there's 7 left that are completely functional and they're not defective. Overall, I have 200 parts and I'm drawing 10. In that particular combination, it's about a 1% probability that I'm going to draw that. Again, you have to have a specific set that you want to predict that you're going to draw. However, this has another interesting application in that what's the probability that I'm going to get everything defect-free out of my 10? If I know that there's some bad ones in there, what's the probability that I'm going to draw 10 good ones? Now that's an interesting question, and one that probably you're going to want to ask. So out of my 6 non-functional, I draw 0. 8 functional but defective, I draw 0. And all 10 of them that I draw are from 186. Now that's not a bad probability though, because that means that I have slightly less than 50-50 chance. The probability of getting some with some defect is the complement of that. So I have slightly higher probability of getting some defect when I draw them out of that, even though 186 of them are good, and only 14 of them have a defect of some kind. I still have a better than 50-50 chance of getting one of those 14 that are bad in some way.
That doesn't make any sense to me.
I mean, I have 10 in 10 draws. But in 10 draws. Okay, but maybe that's a little bit more intuitive. Of just one, no. Because what I would have to do then, if I draw just one, that would be 0, 0, and 1. And that would be, and this would be 200 over 1. Okay. And that would give you a different value, which is lower than that. Make sense? Somewhat intuitive, at least. Okay. We'll talk about it more later. So that's our hypergeometric. All right, let's go to some continuous functions now. Okay. The one that is really easy and which we use constantly is the uniform distribution. Uniform distribution, and it's continuous. And even though it's really dull, it's valuable. It's a function that looks like this. No matter where you are in the function, the probability is exactly the same. And it goes from alpha at the lower range to beta at the upper range. So that means that the probability of getting any value is 1 over this difference. So the probability of getting any value is 1 over beta minus alpha. Very, very frequently, alpha is equal to 0, in which case that reduces to 1 over beta. Very, very frequently, it's alpha is 0. We usually don't use a lower value other than that. The average, as you probably guessed, is right here in the middle. So it's beta plus alpha over 2. And the variance is that beta plus alpha squared over 12. As it turns out, the variance is going to fall about like that. Or actually, variance is going to be, that's the standard deviation. The variance would fall outside. But now what is of more interest to us is the cumulative distribution function. When we get to the continuous variables, or the continuous distributions, the cumulative function tends to be of greater value. F of x, can I get this out? The cumulative function, I'll draw it over here. It's like this. Where that's 1. It's just a diagonal, straight line. One of the things that we like about this is that it's good for chi-squared tests, because chi-squared, you assume that things are normally distributed, or evenly distributed, or uniformly distributed, and then find what the variation is. There was even, and this was quite a few years ago, a uniform distribution Dilbert. Okay? It wasn't explicitly the uniform distribution, but, and I looked for it, I wanted to find it rather than trying to describe it. It's not nearly as interesting trying to describe it, but what happens is Dilbert goes to the manager, the guy with the pointy hair, and he says to him, I just discovered that 40% of our absences occur on Mondays and Fridays. And of course his hair stands straighter up, and he says, you have to look into this. Well, that's a uniform distribution problem, because think about it.
That's fine.
If you have five of them, you would expect 20% every day. So 2 times 20% is 40%. Sounds like a lot when you say it that way, but it's just what you would expect. It's not unexpected. But of course he managed to get his clueless manager up in arms and all excited about it, which I thought was great. I thought that, wow, there's statistics in Dilbert. So anyway, you can, what you could do, however, is say, okay, that's what I would expect for absenteeism. What's the actual rate here? So this would be the expected, this would be the observed, whatever your actual proportions or numbers are, and then you can do the chi-squared. If you recall, chi-squared equals summation of observed minus expected squared over expected, and find out whether you do have a significant variation from a normal, uniform distribution for your absenteeism. Anyway, that's the uniform distribution. It's not overly exciting. However, when we get to simulation, we're going to be dealing a lot with the uniform distribution, because with simulation, when you're trying to generate random numbers, matter of fact, when Excel does it, Excel will generate random numbers for you. I mean, I joke about it all the time about using the Excel random number generator, but that's what it does. And and there are tests where you write a random number generator to make sure that it's uniform. because it has to be uniform. If it's not random. And that's a pseudo-random number generator. It has to be uniform. So we'll talk about random number generation. I'm sure that you're all on the edge of your seat with that, but the uniform distribution becomes important with random number generation. And this is the CDF, and the lower bound and upper bound, in other words, alpha and beta are 0 and 1. And if I have x 0.1, it's going to be exactly the probability that it's less than 0.1 is 0.1. So that you get this perfect straight line that goes from 0 to 1. Like I said, it's not overly exciting, but it does have applications. This is exciting. At least I think it is. And that is the exponential distribution. Remember, I said that the different distributions describe things. Now, lambda in the Poisson distribution is the number of, let's say it's the number of arrivals, okay, during the lunchtime rush between 11:30 and 12:30 on the average per hour, the number of arrivals. Well, this uses lambda, which is the same as in the Poisson distribution. It's the same lambda, Poisson process lambda that you use in the Poisson distribution. They have a relationship with each other. However, the exponential distribution, instead of having this kind of a shape that's discrete, okay, where this is lambda t here, what the exponential distribution has is a continuous shape, which is a decay. Okay? And like I said, that can be used for not the number of arrivals, but inter-arrival times. Okay? That's different. Times. Too many R's in there for me. It can be radioactive decay. It can be an LED decay. As you know, when you turn off an LED, how it kind of fades out. This is the way it behaves in the exponential distribution. And it's continuous because time is on this axis and probability is on this axis. Right. Here, it's the number of arrivals on this axis and probability on this axis. So it's something different. Okay. Here, over time, what I'm looking at is inter-arrival times. Because I have a bunch of people, this is where I said, and you've all seen this, I know, where the line will grow. There was a whole bunch of people come in all at once, and then nobody comes in, and then, or they straggle in, and a whole bunch of people come again. So that means that they have very short inter-arrival times, and there's a lot of them. Whereas when you get up here, the stragglers have long inter-arrival times. So that's what the exponential describes, is something like inter-arrival times. And again, we're talking about event rate and a Poisson process. It's assumed to be constant and stationary. It's not always a good assumption. Sometimes you have to revise it. But if you have one that you believe is constant and stationary, then you can use that lambda for the Poisson distribution and for the exponential distribution. And then the x are the units of contiguous exposure. Those units can be a time, missions, because we can still use missions as units of contiguous exposure. The mean is 1 over lambda, and the variance is 1 over lambda squared. Sometimes that's of interest. This is one that we'll find that almost always we're more interested in the CDF than we are in the PDF. And the CDF gives you the probability of the first occurrence, when that will happen. I'll say that a number of times, but that's what CDF gives you. So, this is a PDF, exponential PDF. This is a decay with our shuttle data. okay? The number of missions, the expected number of missions is 56, and that falls right in here, expected value. And that's the variance, not particularly interesting. But this is the probability of, of occurrence of the time between crashes. Okay? So that as this probability decreases, there's more time in between the crash, just like there's more time in between arrivals. Okay? And you can model that continuously. This isn't as interesting for our applications, however, as the cumulative distribution function. What this tells you is what is the probability of having T missions before the first crash occurs. Okay? Wait a minute, did I say that right? The probability of the first crash occurring, no, I didn't say it quite right. What's the probability of the first crash occurring by T missions? So the probability of it occurring by the first mission is essentially lambda. Okay, so first crash occurring on the first mission is essentially lambda. On the second mission is 0.3, and it grows. As I accumulate, this is what's intuitive about this, because the more missions I have, the higher the probability grows that it will be the first crash since the last one. So by the time I get to 40 missions, I'm at about the 50-50 rate.
I don't want to be the pilot on that.
That's right, that's right. And then and it grows beyond that, once again, to infinity, because this has no upper end and it asymptotes to 1. It never reaches 1, but it asymptotes to 1.
So you could use this for like the airline industry? So you have like one accident every 200 flights
If-
and
If you believe your lambda, yes.
But your lambda can be derived from, you know, a fairly large chunk
Yeah.
of time.
That's right.
And, you know, there's like, you know, when CRM was introduced, lambda probably changed because it was a major change to how the airlines did business.
If you collected data after CRM was implemented and before, and you believe that that's different enough, yes, absolutely. An application, and this is where half-life comes from. You've all heard the term half-life in relation to radioactivity. Half-life assumes that 50%, there's a 50% probability, or 50% of the particles will have dissipated, will have been emitted by the time it reaches whatever that half-life is. And the way you derive it is you set the cumulative distribution function of the exponential to 1/2, and then you solve it for t. Okay? You can measure the rate. Lambda is the rate of emission of radioactive particles. You can measure that. You can over a relatively short period of time. You know what lambda is, okay, because it's constant. Radioactivity is remarkably constant, and so that you can calculate lambda, and then you solve this, and you set it equal to 0.5, and you solve it for t, and you know then you'll find out what the half-life of that element is. Carbon-14, for instance, the way we carbon date carbon-14 is known to have a decay rate equal to this. Okay, and the half-life, and this is in terms of thousands of years. It's 5,735 years, I think. But you can calculate the half-life, this lambda. And what I did is I found out what the half-life was, and then I calculated lambda from it. But the way they calculated, the way physicists calculate half-life, is to determine what lambda is, and then calculate half-life from that. And if you look at the exponential, just the exponential PDF, and graph it with those variables of lambda and to infinity, and this is in thousands of years, remember, you can see that at about 5.73, about in here, is where roughly half of it would have been emitted. Okay, the radioactive particles would have been emitted by its source. And because lambda is so constant, that's why it can be used for radiocarbon dating. That's why it can be used for applications like that. Okay? And there are other radioactive, there are other elements that can be used in similar ways. Potassium argon, for one, is another used for much longer periods of radiocarbon dating, or radioactive dating. But anyway, this is one, and I just thought that was interesting because that is a very common application for the exponential distribution, is radioactive decay. And you can calculate half-life just by collecting data on the rate of dissipation. And that is the 50% mark. This is the exponential CDF. 50% would have dissipated by the 5,735 years, whatever it is. You can see that that cross is about right there. Anyway, I think that's an interesting application. Not the one that we're going to be using necessarily, but it's nevertheless shows some the variety of which applications. This I thought was just cool, so don't worry about this too much. First of all, I wanted to talk about what a gamma function is. Okay? This is a gamma function. Okay, it's such a complex function that it has imaginary numbers in it. You guys know what imaginary numbers are? Okay. I'll take that for it's the numbers that I give you on exams, right? No. When
It's the numbers we give you on it.
That's probably closer to the reality. But anyway, when you're solving differential equations and quadratics sometimes, the only way to solve it is to factor out a square root of -1, which you know doesn't exist, right? So -1 is I. It's an imaginary number. And so what mathematicians have done is they've taken an entire axis of imaginary numbers that are based on the square root of -1. And like I said, it's the only way to solve some things. And I know that it works. I don't quite understand totally why it works, but it worked. I mean, I took a whole semester of differential equations, and we were always using that. And I could see how it worked, but it takes a really good imagination to imagine the square root of negative numbers. But anyway, the gamma function has an entire axis of imaginary numbers, of I. And where did I see it here? This is the imaginary axis right here. Okay, the height they've graphed is an imaginary axis. So when you solve this, you can't solve it without that number. Fortunately, if z is a positive integer, this is uppercase gamma of z. This is the function. If z is a positive integer, which it will be for us, lucky for us, then this reduces to this. It's just a factorial. That's all it becomes. And we don't have to worry about imaginary numbers or any of that. But like I said, I thought this was just so interesting that I tossed it in here as an introduction. I'm not going to test it on it, so don't worry about it. But gamma of z, when it's a positive integer, is just the factorial of z minus 1. That's the only function we're going to be interested in for our application. But anyway, there is a gamma distribution, and gamma of r is always a positive integer. So it's always going to be r minus 1 factorial for us. What does the gamma distribution do? What it does is it allows us to model a number of parallel exponential distributions. So, if I have a parallel series, or a parallel system set up, well, I won't draw it because it's on the next slide, but where I have lambda, it's the same lambda as we were talking about in the exponential and the Poisson distributions, all right? But it becomes an event rate, but it now is also called a scale parameter. Okay? We have R, which we call a shape parameter, which means that it is the number of exponential components that we are dealing with simultaneously. When R equals 1, this reduces to an exponential distribution. Okay? This is lambda times e to the minus lambda x, because this goes to 1, because r minus 1 is 0. Anything to the 0th is 1. Lambda of r minus 1 is 0 factorial, which is 1. So it's just lambda e to the minus lambda x, which is just the exponential distribution. Okay? And then x is our random variable, which I will talk about in a little more detail. But notice, e of x for the exponential distribution is 1 over lambda. For the gamma distribution, it's r over lambda. For the exponential distribution, the variance is 1 over lambda squared. For the gamma, it's r over lambda squared. So it's just r exponential distributions. And whenever it's just 1, when r is 1, it becomes exponential. So that's the whole point. Cumulative, we model this as a Poisson. Okay, it becomes much less intractable if you model it as a Poisson for cumulative. And that's one we're going to use. So this remembers a Poisson. Lambda x to the k e minus lambda x to the k factorial. Right. Yes?
What's the K again?
K is the number of exponential distributions or exponential components that we're dealing with simultaneously. Let's look at an example. Oh, actually I'll come back to that. For one thing, if lambda is half of 0.5 and r is nu, as in the number of degrees of freedom, over 2, then this reduces to a chi-squared distribution. And that's where we get the chi-squared from the gamma. Just a bit of trivia, don't worry about it too much. This do worry about. So let's say that we have a parallel components where we have 3 components. Each one of those has a failure rate of lambda. It's the same failure rate, same components. And we have a switching system, which as soon as unit 1 fails, it switches to unit 2, and then when unit 2 fails, it switches to unit 3. Okay, so it will automatically switch from 1 to 2 to 3. Each one of these individually is exponential, the failure is exponentially distributed, failure rate. Now, and I know that those failure rates is 0.01. Okay, so that means that r equals 3, because I have 3 components, each with its own exponential distribution. I have a single lambda because all of them are identical. And what I can figure out then is what the reliability of this system is. If it's predicated on this decision switch, that switch works perfectly. When 1 fails, it switches to 2. When 2 fails, it switches to 3. It works all the time. It's a little bit of an abstraction, but nevertheless. So, the reliability, notice that the CDF is the probability that x is less than some value is 1 minus, okay? What we're interested in is reliability. And that's f of x. Remember that. Reliability is 1 minus f of x. So that means it's 1 minus the Poisson formula. So that means it's just the Poisson formula for reliability. That's all you need to remember, but that's how you derive it. Okay, so for the reliability, it's a formula. It's not 1 minus the formula. It's the end of the distribution that we're interested in, or whether we're interested in failure or success. Reliability is success. F of x you can think of as failure. And because it's f, it's not the intention, but you can think of it that way. Okay, so lambda times, what's probability that it will function at least X hours. Okay, X is our exposure variable. And I didn't expand it beyond X hours. We can, but it's kind of trivial to do that. But let's take a look at it first. Let's first get from here to here. So it will go for each one of our components, from 0 to r minus 1. And so for k equal to 0, that's 0.01 times x to the 0. I'm going to write it out, even though that goes obviously to 1. E to the minus 0.01 times x over k factorial, which is 0 factorial. Okay? So that's for 1. For k equal to 2 plus, I'm sorry?
That's for K.
This is for k equal to 1. Or k equal to 0, I'm sorry. Okay? And then you add, and this is for k equal to 1, 0.01 times x. Well, I should do it this way. To the first, e to the minus 0.01 times x over k factorial, which is 1 factorial. And then for k equal to 2, r minus 1, that's 0.01 times x times to the squared, e to the minus 0.01 times x over 2 factorial. Okay. Now, well, the first thing that all of these have in common is the e to the minus 0.01 to the x, so you can factor that out. Okay. Does everybody see that? I'll circle these so you don't get confused if that's part of the equation. It isn't. So each one of these terms has e to the minus 0.01 times x common to it, so you can factor that out. So do this. So the first thing we factor as is minus 0.01 times x times, if I factor that out, that's 1 over 1, so that's 1. Plus, that's just 0.01 times x over 1. So it's 0.01 times x plus 0.01 times x squared over 2. That's here. So, all I need to do is figure out how many hours I'm interested in modeling. If I want to know whether it's going, what's the probability of this, what's the reliability of the system over the next 100 hours, I substitute 100 in for x and go ahead and do the calculation. I want to know what the reliability of it is over the next 1,000 hours. I substitute 1,000 in for x. Make sense?
Is that, in your last 0.01 times x squared over 2, is that x supposed to be on the inside or the outside of the bracket? Does it matter?
It doesn't matter, but
Okay.
that does matter.
Okay.
It's supposed, well, actually, that doesn't even matter. No, you can do it any way you want to.
Okay.
So what this really, what we really get out of this is a number of parallel components or components that can be thought of as being parallel. Each of them with the same lambda, and the reliability how it's going to increase the reliability of the system. As you increase components, you'll find that the reliability increases. By just one component, it's just exponential. If I have two components, then I have a slightly better. If I have three components, more stuff. What might be interesting is to derive what our equation would be with four components, and really all that would be is 0.01 x to the third over 6, right? But it would add another term with four components. So far, so good? Or what the hell is he talking about now? Sort of. That's right, pretty much what the hell is he talking about now? Anyway, let me go back here, now that I've talked about it. Remember I said that lambda is our scale parameter and R is the shape parameter. Okay? As we alter lambda and R, you can see that in this case, this is the legend for this, this is the legend for this. And for some reason I couldn't get the legend in Excel to keep my Greek letters, so that's why it's a little bit Roman L rather than the lambda, I don't know why. But anyway, as you adjust the shape parameter and keep the scale, and also increase the scale parameter, you can see that the influence that it has is to change the shape, because lambda 1 here and lambda equals 1 here is a very similar shape. And as you increase lambda, the scale just shoves it up. Okay, so it's just shifted in that direction. And here, it's shifted further in that direction because our shape parameter is so altered. So you can look at the lambda equal 1 as the gray, the lambda equal 2 is the blue one, and that changes in scale, but also changes shape pretty substantially. So as you adjust the shape and scale parameters, this distribution is going to look substantially different. Now for the CDF parameters, it's a little bit more obvious because it asymptotes to 0. And here, the shape and scale parameters press it close to 0, the scale parameter. In both cases, in all cases, the gray presses it closer to 1, or presses it closer to 1, I should say. And I tried to adjust these so the scales all the same, so it's comparable. So this is how the shape and scale variability affects the CDF. And we have one more distribution, so let's just go ahead and plow right through that, and then we'll talk about all the problems next week and see how this and review these. This is the Weibel distribution. The Weibel distribution, look at the CDF, because again, CDF is what we're interested in. Really what it does is it takes the exponential distribution and kind of tweaks it by giving the exponent of the exponent another exponent. So it raises the exponent to a power, therefore adjusting it somewhat. And there is experimental data for, especially in reliability engineering, that I'm going to show you in a minute, that will give you the appropriate alphas under different circumstances. So here, the alpha is the shape parameter, and when that equals 1, and if beta is 1 over lambda, the MTBF, then that becomes the exponential distribution. But this is like the gamma. If the shape parameter is 1, it becomes the exponential distribution. So anyway, the alpha, if that becomes 1, it's the exponential distribution. If it's something else, then it's a different distribution. And beta is the scale parameter, and it is the mean time between failure. It's 1 over lambda. Yeah, I didn't write 1 over lambda for beta, but that's what it is because you know what the MTBF is. And X are units of contiguous exposure. This I put in just because I thought you would be really interested in it because the mean and variance of the Weibull distribution is outrageous. And that's the way that you calculate. You have to use the gamma distribution to calculate the mean and the variance, and if it's not a positive integer, which it's obviously not going to be under most circumstances, those become very ugly to calculate. So I just put it in there to illustrate it. This is rainfall. Okay, 1 day's worth of rainfall. And modeled as a Weibull distribution, which is not too bad, just with a 95% confidence limit, or 90%, sorry, confidence limit. So I ran across that looking around. I thought that was an interesting application of the Weibull distribution. So let's look at, this is my graphs of the shape, of adjusting the shape and scale parameters, what they look like. You'll notice that the cumulative for both gamma, exponential, and Weibull look awfully similar, and that's for a reason. This is, I took this off of a website called Behringer. I don't even know what Behringer does, I just ran across it. But the component, the alpha and the MTBF, or beta, whatever lambda, values for different components. Okay? And they have, what low and high I suspect is 5th and 95th percentile, and this is the mean. But what that means is the shape factor, if that's less than 1, it means it's going to have a failure early in its life. Okay? A failure greater than 1 means it's going to have a failure later in life, or an alpha greater than 1. And if you look at alphas greater than 1, then here, whenever alpha, once again, I couldn't transfer alpha, but when alpha gets to 1, then it's that's the deflection point. But the failures occur later in the distribution, and that's even more obvious for PDA. Because then it will peak rather than being a typical exponential shape. When alpha hits 1 and goes beyond it, then it starts to peak later. And that indicates a failure later in the life of the component. Okay? And what that is useful for, oh, and by the way, when alpha equals 1, that's called an exponential distribution. And another distribution that I'm not going to talk about, but when alpha equals 2, that's a Rayleigh distribution. So it has its own distribution associated with it. Early and later failure are related to this phenomenon called the bathtub curve. And the bathtub curve talks about the failure of components. It has to do with, and it is actually true for organisms as well. It's called, so at the beginning is infant mortality, normal life, and then death at the end of your life. Okay? We have higher death rates early and later in life than we do in the middle of life. And that's, and components behave exactly the same way. I mean, they will have, if an electronic component is going to fail, it fails at the beginning, or it fails when it's getting closer to its expected failure, its mean time to failure. Right? And this is called a bathtub curve. And you can model that largely using the Weibull distribution, because this is early failure, and this is late failure, by adjusting the alpha. You can also use exponential here, because that's a variant of the Weibull. You can use uniform in here, and possibly quadratic out here. But Weibull is useful in that you can apply it to the entire life of an organism, component, whatever.
Waldock uses this.
Bathtub curve, or does, okay? Does it talk about the Weibull distribution?
Nope.
Well, that's what it is. That's what it is. And this is an example. It's not, I'm thinking of changing this, but this is a the adjustment of shape parameter to silicon wafers and the time required for the process. And it's kind of a plug and chug example, but it gives you some something that will show you an application. But what would be best is if you want to understand the probability of failure is to go back to something that will give that data have been collected on the shape and scale parameters, and use that as the probability of failure in a certain amount of time. But really what you're interested in, as before, is the probability of failure in a certain time period. And again, the reliability here is 1 minus this. So the probability of failure is 0.03, let's call it 0.04, and the reliability is 0.96. With good reliability over 10 seconds. The probability that it'll take less than 10 seconds is 0.04, probability that it'll take more is 0.96, sorry. Questions? Next week, I will finish the homework for topic 2, and I will go over the practice problem set 1. And if it appears that everybody is comfortable enough, we'll go ahead with the exam in 2 weeks. However, if there is a massive revolt, I'm open to having the exam later than that if you don't feel prepared. So that's the advantage of a small class, is we have a lot more flexibility. Okay. If you don't have questions, you go off and do wonderful things, and we'll talk about it next week. All right.
Are you planning on doing a study session?
I can if you want me to. Okay. I'm more than happy to do an extra session.
Like Monday or whatever.
Yeah.
Tuesday.
Monday or Tuesday evenings, probably either one would be good. Let me look at my calendar and then ask you next week again. Okay.